We're looking into Exergy, reversibility, isentropic efficiency, and second law efficiency. So we have seen entropy and entropy generation. We have seen that the entropy of the universe in the thermodynamic sense is composed of the system and the surrounding. So the system and surrounding combined, that is the universe. The entropy of the universe is increasing. Mm, yeah. So we look into Exergy. So what is Exergy? So Exergy is it is represented by the Greek letter phi. That is the maximum positive work that can be extracted. Maximum positive work that can be extracted from a system when the system interacts with the ambient atmosphere and reaches a dead state. So we'll qualify what a dead state is. Before that, this is the maximum positive work that can be extracted from a system when the system is operating in between a high temperature reservoir and low temperature reservoir and execute a cycle. Suppose consider we have a reversible cycle. We know that the efficiency of a reversible cycle is the highest. So if we have a reversible cycle and it's putting out work, and if this is Q1, this is Q2. So we know the efficiency for any generic cycle is written as 1 minus Q2 by Q1. So we are trying to find the limit for this. So we are trying to find the limit for this. The limiting case is when either first condition is when Q1 tends to infinity. If Q1 is very large, we can see that this term will go down. Thus, the efficiency tend to go to unity. Okay. Or the second thing is we want Q2 to be very small. Q2 to be very small. So Q2 tends to 0. But this is like impossible. So that is, if Q2 is 0 Kelvin, then we'll have 100% efficiency, which is impossible. So in a general sense, to obtain the highest efficiency without spending any other work, the region where we can reject heat is to the ambient atmosphere. So in that sense, Exergy measures what the maximum work that we can obtain without bringing the temperature of the system down. For reversible system, the ratio of heat transferred is proportional to or is equal to the ratio of temperature of the source and sink. In that sense, if we don't bring down, or if we don't use any additional work to bring down the temperature of the sink, if we don't use any additional work to bring down the temperature of this sink, the maximum work that can be obtained is by exchanging heat from high temperature reservoir and the ambient atmosphere. So once the system state reaches the ambient atmosphere, it'll not have any other potential to do work. Okay, if the temperature of the atmosphere is T0, if the pressure is P0, and if the system's temperature also reaches T0 and its pressure reaches P0, then the system can't expand because there is no change in pressure. So and there is no change in internal energy between the system and the surrounding. So the system cannot do any extra work to the surrounding, or the surrounding can't do any extra work onto the system. So this is in a mutual equilibrium. The system and the surrounding has reached a mutual equilibrium. This state is called as a dead state. Okay. So again, we'll consider a Carnot cycle, which is operating between the system, which is operating between a high temperature reservoir and the sink. The sink in this case is the ambient atmosphere. In that case, we can write the work output from this Carnot cycle is given by WR is equal to Q minus Q0. Okay, and as this is operating in a cycle, and this is a reversible cycle, Carnot's engine is a reversible cycle, so we can write the entropy as is equal to cyclic integral of ds is Q by T. This is the high temperature reservoir minus Q0 by T0. Q0 is heat rejected to the cold or the ambient temperature. By T0 is the temperature of the temperature of the ambient atmosphere. So cyclic interval of ds should be equal to 0. So this is equal to 0. So we get q by t is equal to q0 by t0. This is very similar to what we observed in the case of the absolute temperature scale. So we can write the efficiency eta therm is equal to W max. So the maximum, we know that the maximum efficiency is obtained for a reversible cycle. So eta R therm will be maximum under any condition. So eta therm for reversible cycle is equal to W max by Q. This is equal to 5 by Q. Okay, by definition of Exergy, the maximum positive work. Okay, so eta term is equal to 1 minus q0 by q is equal to 1 minus t0 by t. So phi, the Exergy, we can see here that the Exergy is equal to q into, sorry, we can see that the Exergy is q into 1 minus t0. So it is just a fraction of what q is. Okay, we can see that as t decreases, q increases. As this t0 decreases, q increases, and as t goes to infinity, phi increases. Okay, so that's what we mean by Exergy. Okay, so Exergy is also called as available energy. If we just draw this in like for a single process, if I just draw this in the case of a single process, so suppose I have something like this. This is a single process in a PV diagram. This is a PV diagram. We know that the area under this curve is the work done. Okay, so at a particular pressure and temperature, say somewhere here, this would be the ambient condition. In a TS diagram, if I put it in a TS diagram is much more simpler for a Carnot engine. Okay. If this is T, this is T0, we know that this is the heat, quantity of heat. In a TS diagram, the area under the curve will give us the heat input or heat rejected. So here we can see that T0 would be the limiting condition, or below that T0 that much amount of heat has to be rejected to the ambient like to get maximum work. Okay, so this puts a restriction on the amount of work that can be converted to heat, amount of heat that can be converted to work. Okay, whatever, even if it's a reversible cycle, there is a restriction on the amount of heat that can be converted to work. Thus this gives a classification of grades of energy. This is thus as the entirety of heat can never be converted into work. Heat is considered to be a low grade energy, and as the entirety of work can be converted to heat, work is considered as a high grade energy. Okay, this is just a classification of energy on basis of grades. Okay, that is for Exergy. So delving a bit deep, we'll be looking into irreversibility and so on. For that, we'll consider a closed system where heat transfer occurs isothermally. Okay, so this is critical because we'll be looking into heat transfer that is occurring isothermally quite a bit, because though it is impossible for heat transfer to occur isothermally, we'll assume that heat transfer is occurring isothermally by via a quasi-static process. Okay, that is the temperature of, suppose we have a source which is placed in close proximity to a system. This is the system, this is the source. We assume that the temperature of the source is a bit higher. than the temperature of the system. Okay, so we have this is a quasi-static process, thus we have weights here. So due to this small temperature gradient, heat is being transferred to this from the surrounding to the system. So this causes the temperature of the system to go up. What we do is we remove weights in such a way that the temperature inside the system will remain constant, but other parameters will change. That like the pressure and temperature will change. So we maintain the temperature inside the system constant. So this temperature differential dt is assumed to be very small. Hence, this is assumed to be a quasi-static process. Hence, in the limit, this is a reversible process. This is the only way we can achieve a isothermal process, theoretically. Okay, so we here oftentimes we'll assume that we have an isothermal process. So suppose we have a reversible process which is occurring between like connecting two states, state 1 and state 2. By energy balance, we can write the change in internal energy is equal to the difference in heat and the work heat supplied and the work net heat supplied and the net work output. That is a change in internal energy. And for entropy balance, we can write this is for irreversible system. This is for a generic process, and for the entropy. So we know that for a irreversible cycle, delta S is written as is always greater than integral of dq by t or delta q by t. We know that. The thing is, to remove this equality sign, what we do is we add a term to right side. Okay, because dq by t is always less than ds. So if I add something like sg, which is a entropy generation term to this thing, we can match this quantity. We can put an equality sign. This is an arbitrary quantity. Currently, we don't know what this is. Okay, this is for entropy balance. So if as I mentioned earlier, if we have a reversible process, this is 0, or SG, the source generation term, entropy generation term is 0, but the rest is the same. Okay, so we try to find an equivalent reversible process because we have no idea how to compare between this reversible process and this irreversible process. So what we do is we try to find an equivalent reversible process for this cycle. Okay, such that the only term which currently we are looking into is this entropy generation term. If we can somehow make this entropy generation term into a whatever, into a parameter associated with the system, in as it executes a cycle, that will be 0. Hence, we can assume that the equivalent cycle becomes a reversible cycle. So we try to fix this by like thinking of ways of how to make this thing a property of a system. Okay, so the thing is, in most systems, like even in case of like open system or closed system, there will be entropy associated with the process. Entropy associated with the process because as the state changes, there will be entropy change in entropy. The second thing is there is entropy generation and there is entropy transfer. The entropy transfer is associated with the heat transfer. Okay, so here entropy as change associated with the process cannot be changed because that will cause the change in state, but entropy transfer we can fix. So that's what we do here. What we do is we assume that this entropy generation is due to the exchange of heat from the system to the ambient surrounding. Okay, so the amount of heat exchanged by the system and the ambient surrounding is assumed to be something like Q0, and this is assumed to be reversible because this occurs in an isothermal way. So the amount of heat exchanged between system and surrounding isothermally is Q0R. Okay, and we know that if this is a reversible process and this occurs at a constant temperature, the entropy change or delta Sg is written as Q0R by T0, or Q0R is equal to T0 delta Sg. Okay, so this somehow fixes our equivalent systems entropy. So we get the equivalent systems entropy. I'll put it as equivalent. Delta S12 is equal to integral 1 to delta Qt plus Q0 by T0. Okay, so the problem is we have injected heat generation term into our system. That is, we have assumed that the cause of entropy generation is the exchange of heat between the system and the surrounding. Okay, so we have to account for this heat exchange into our energy balance equation. Okay, that's what we do here. So this is our generic reversible system. So here we inject this heat input term so as to account for our assumption. Okay, so what we get is something like W12 equivalent. This is reversible equivalent cycle is equal to W12 irreversible plus Q0. Okay, this is quite significant. So we have just what we have done is we have just formulated the equivalent cycle, which is equivalent in the sense that its entropy in the cycle is 0. Okay, somehow we managed to make its entropy in the cycle 0. So what we can see here is even like even in that condition, we have created an equivalent cycle whose work output is higher than the reversible cycle. Okay, so how much is it greater than the reversible cycle? If you ask, that is Q0R. Okay, what is its significance? So its significance is that even if we consider an adiabatic process, because an irreversible adiabatic process is assumed to have no heat transfer, but if we formulate an irreversible, if we try to formulate an equivalent cycle for that or equivalent process for that, what happens is we have to take into account this Q0R term. Okay, so an equivalent adiabatic system, or if we have an adiabatic process or irreversible adiabatic process, if we try to formulate equivalent system for that, equivalent reversible system for that, we have to take into account that there is heat transfer. So an adiabatic process in its equivalent form will never be adiabatic. Okay. So this is just manipulation of the above equation. So delta Sg is equal to delta S12 minus delta Qt. So that's from this term. Delta S12 is equal to integral of delta Qt plus this thing. If we have a isothermal process, we can write something like this: isothermal heat transfer. Because obviously, for any reversible cycle, we can assume assume that it has an equivalent Carnot cycle. That is from Carnot theorem. So we can just rewrite Q0 like delta Sg as Q0 by R is equal to delta T S12 minus QR T. This is the reversible heat transferred. This is equivalent. Everything is equivalent. So Q0R is equal to T0 delta S12 minus QR T0 T. Okay, so substituting what we have, like W12 equivalent is Q12 minus delta U12 plus this is the Q0 term that we said that we have to take into account for energy balance. So we just substituted what is Q0R term here and just shuffling, we get W12 is equal to delta 12 plus T0 delta S12 plus Q12 into 1 minus T0 by T. Okay, so this is the equivalent work done by a reversible process which is operating between the same state points. Okay, so taking a slight detour, we'll just look into what irreversibility is. So irreversibility is the difference between an equivalent cycle or equivalent reversible work, or cycle or a process doing equivalent reversible work, and the actual work which is irreversible, okay, which is obtained when the process occurs between the same state points. That is, it starts at P1 T1 U1 H1 S1 and ends at P2 T2 U2 H2 S2. These are state points. So if we have 2 points 1 and 2, we compare between the irreversible process IRR and we compare between an equivalent reversible process that is occurring between these. So we obtained this equivalent reversible cycle by manipulating the entropy generation term. So this is it. So 1 minus WR equivalent minus WIR. So what is this? This is T0SG or Q0R. So this is the representation. So we can see from the above equation itself, this is the irreversible work done. So the irreversibility is given by T0 delta S12 minus T0 Q12 by T1. Okay, so this is for a system interacting heat with a single reservoir. So if we have multiple reservoirs, that is, if I have a system that is interacting heat with multiple reservoirs with multiple boundaries, we can write something like this. That is, irreversibility is equal to T0 delta S12 minus T0 into Q1 T1. So everything is assumed to happen at isothermally. So Q1 T1 plus Q2 T2 plus etc. Okay. So this is regarding irreversibility. So next is we'll look into isentropic efficiency and second law efficiency. So like I haven't mentioned what this is. So this is Exergy. So Exergy term, we looked it into Q into 1 minus T by T0, and we have said that it is the maximum work that can be obtained when the system is operating between a high temperature reservoir and the ambient or the dead state. So when the system reaches its dead state, its pressure reaches its dead state, that is P0 value, and the volume may reach maximum value. That is, we want work output, so the maximum work output would be obtained if the volume of that particular closed system or the piston cylinder arrangement reaches a maximum value. So that value is given by V0. Okay, so phi is equal to, so this is the equation for phi. U is the internal energy at the starting state, S is the entropy at starting stage, V is the volume at starting stage. The rest of the terms with zero subscript, these are the terms that represent the dead state. Okay, so the maximum work output is obtained from this thing as it exchanges heat with the ambient. But if we have a system which is not exchanging heat with ambient, if it is starting from a high temperature reservoir and rejecting heat to a low temperature reservoir, the maximum work that can be obtained between that process can be obtained by the difference in like exergy between these two states. That is written in this equation. Okay, so WR max is equal to 512. So the irreversible work obtained in that case is given by the reversible work minus I, where I is the irreversibility. So this is just a detour. Okay. So next is we'll look into what isentropic efficiency is. Isentropic efficiency is defined for a process. Usually it is defined for a process. So if we have a process that goes from state 1 to state 2, so we can find the work done by like finding in a PV diagram. We can find the area under the curve. Like we have equations for that. For any arbitrary process, we have P dV, integral of P dV as it goes from state 1 to 2. We can substitute how P is related to V. So in case of an this is for a generic process. Okay. So in case of an isentropic, we consider an isentropic process which is happening between these two states. That is, we consider an isentropic process. So this is not an isentropic process. This is just drawing. Just for drawing sake, we'll just show that this is an isentropic process. Okay, and we find the work done between these two states and what the work done and what the work done is in that reversible isentropic state. Okay, and the ratio between these two, that is the actual work obtained from that process and the work obtained if the process is isentropic, that ratio is called as isentropic efficiency. Okay, this is used in case of turbines and things like that because it is quite significant. It is a measure of irreversibility. Next, we'll look into second law efficiency. Second law efficiency is nothing but what we have learned till now. That is, we compare what if we have a cycle or if we have a process, we compare what work we get between two states or in a cycle, and what work we could have obtained if it was like an ideal process or an ideal cycle. Okay, so if we have state 1 to 2, this is just a process. We compare what W actual is with delta phi being the maximum available work. So that is what second law efficiency defines. That is the ratio between actual work and the maximum possible work that could be obtained between those two states.